I think it's about time to get started. Sit. And first, thank you for coming on this Saturday noon talk about doing fun stuff with Unity3D and machine learning. My name is Chatzizaharias. Maybe a little bit of contradiction there between the first and last name. I'm half Dutch and I'm half Greek. My Greek side of the family lives in Kos Island in Greece. If you were searching for a vacation destination, it's the best island in Greece, so go ahead. I live in Utrecht, the Netherlands. I think I heard some Dutch here, so... I have a couple of hobbies. I like bouldering, I like tabletop games, and maybe not entirely unsurprising, I am a very vivid gamer. I game a lot. Anybody else that likes to game a lot? Good, then you're in the correct talk, I can tell you. I work for a consultancy called J-Driven, which is pretty small, 30 people in the Netherlands, and at the moment I consult as a backend software systems engineer at routscanner.com, which is a subsidiary of the Port of Rotterdam. It's pretty cool. So that's pretty much all I have to say about me. Now, why this talk? I think we can all agree that artificial intelligence is pretty hype right now, right? With ChatGPT, AutoGPT, etc., etc. Well, some time ago I decided, okay, maybe I should look into this, try to understand how it works, maybe a little bit. So I got into machine learning and tried to understand, okay, how neural networks work, how you can train algorithms to train themselves, pretty much. And then, you know, you go online, you search for all kinds of tutorials, and then you get the tutorials that say, okay, here you have an algorithm, train it to detect kittens in a picture, you know, stuff like that. Well, I said I was a gamer, and if I don't have a dopamine hit within 1 second of doing something, I lose any interest. So I decided, okay, I need to do something with games. So that's why I went to Unity. I have a little bit of background in game development to do it in a more visual, fun way where I could incorporate explosions as quickly as possible. So this is also a little bit of the reason that I'm giving this talk. Hopefully I can inspire some of you to also try out Unity and learn machine learning this way. And who knows, maybe you'll revolutionize the industry. Maybe one of you will make the next game GPT or something, I don't know. All right, so machine learning in games. I think by now a lot of people have a basic understanding of what machine learning can be used for. If you follow talks in the banquet or the other halls, you would have seen the text speech underneath the presentations. So that's done with machine learning, image recognition, about Tesla cars, etc., etc. It's being used all over the world, but not a lot of people talk about machine learning in games. Does anybody have any idea how you could use machine learning in games? Any clues? Yeah? Bots, yeah, NPC AI, that's a pretty good one. That's also the first one, so that's good. Indeed, bots, NPC AI, so there are games out there, for example, Planetary Annihilation, that uses machine-learned AI to have more believable agents where the players can fight against, which, well, it is believed to enrich the perception of how cool people think a game is. Any other ideas? Give this up, we're going perfectly. Yes, procedural content generation. Minecraft is a big example of those. I don't know if anybody here plays Minecraft. Maybe? A very popular game, and there are, well, Minecraft has experimented with it, of course, but there are also games, I think Darkest Descent, it's called, where they basically train machine learning algorithms to generate the procedural content for them on the fly, while making sure that the content generated is playable, that it's actually doing what it's supposed to do. Because the problem with Minecraft is that you can get a world that it's pretty much unplayable if you're a new player, right? Number 3 out of 3? Ah, close. Now, player simulation. A couple of years ago, it was going all through the news that the AlphaGo AI beat the best Go players. But what was bigger news for me, I play a lot of Dota 2. I don't know if anybody can relate here. But a couple years ago, OpenAI made bots or, players, AI players for Dota 2, which is a 5v5 game. So it was pretty impressive that for the first time, you saw 5 machine-learned agents work together to play Dota against 5 real players. And the AI actually took a couple of games from the world champions back then. So that was pretty cool to see. And well, for the rebound, anyone? You got scared, huh? Now, the automated game testing. King is, for example, using machine-learned agents to test Candy Crush, a pretty popular mobile game, in case you haven't heard of it. So they are basically creating, well, what in the backend world you would say integration test. They're using machine learning agents to basically test from the UI side all the way to the backend system side to test their game. That's pretty cool. So Unity, being a game engine, thought, okay, we need to do something with this. We need to have some kind of package that enables machine learning for our users. Anybody here that has used Unity before? Great. Anybody that has no idea what Unity is? Okay. Good thing I have an explanation slide. So Unity is a game engine. Well, it started as a game engine, but right now you can call it more like or they like to call it more like a 3D development engine. You could say it's a market leader. I think, especially on mobile, 80% of the games made are made with Unity. You script it in C#. So I know the Java world isn't necessarily fond of C#, but it's so similar. It's like almost a copy, you could say, and you can get into it very quickly. And I think the strongest strength of Unity is the build once, deploy anywhere principle that they really adhere to. So you have one code base that you can deploy to iOS, smartwatches, smart TVs, Xboxes, Nintendo Switches, you name it. And actually, it works so good that I know of companies that use Unity for their normal business apps, so to say, just simple 2D interfaces, because the build once, deploy anywhere works so good. So a couple years ago, they released a package. They called it the ML agents, machine learning agents. It's completely open source. You can find it on GitHub. It's built on top of PyTorch, and PyTorch is probably the de facto machine learning Python library out there. PyTorch supports a lot of algorithms, but machine learning agents support deep reinforcement learning algorithms and imitation learning algorithms. You can access it through a low-level API if you're really hardcore. And it has also more accessible entry point through the Unity editor, which we'll be using today. It's released in 2017. Since then, it's got quite a lot of updates. But since last year, Unity has been going through some restructuring, some controversial topics, you could say. And it's slowed a little bit in development. But they've said that they're going to pick it up again soon. If you want to get started with this, this is actually pretty cookie cutter. You install Unity. You install Python on your machine. Then you install the Unity ML agents package, which is, through the package UI manager, which is basically Gradle of Maven or Maven for Unity. Just a side note, it's still experimental, so you need to enable preview packages in your editor if you're going to get started. Just Google enable preview packages and you'll find it. And then you can install the ML agents Python package through pip, which is the Python package manager. All right. So how does that all work? You're going to have a learning environment, which is Unity. Outside, you're going to have a servlet running your Python trainer. And that servlet through the API is going to be talking to your learning environment through a communicator. So this is basically how it works underwater. You won't be seeing much of this at first. But it's good to know. So the learning environment has a couple of things. First, it has the communicator, which is basically some code that receives and sends messages to the Python trainer. It has an awesome behavior. That is mostly what you'll be tinkering with. That is attached to some awesome agents. Agents, you can say those are the machine learning entities that will be walking, shooting, doing saltos, you name it. And the behavior is what is responsible for gathering observations that the agent is doing and sending actions to the agent to act upon. Instead of the communicator, you can also use inference. And inference actually means you have a pre-trained model, it works, finally, so you add it to your behavior, and that model is what controls the agent. And finally, you can also use heuristics, which are mostly for debugging. So you can assign normal controls, WASD, mouse input, controller input to your agents to mostly test if collisions and whatever you expect to happen actually happens in the scene without having to start the trainer and hoping that your agent gets where it's supposed to go. There are two training methods, reinforcement learning and imitation learning. I think they're pretty self-explanatory, right? The one tries to imitate something you have pre-recorded, and for the other one, you punish or you reward whatever you want to punish and reward. When it comes to algorithms, there are quite a lot of them supported. Proximal policy optimization for reinforcement learning is very cookie cutter. It has been shown to be working a lot of the times without needing a lot of config. And soft actor critic is an off-policy algorithm, which is very good for learning from past experiences. So you can use a soft actor critic algorithm when you have a very small sample set of data. Imitation learning, behavior cloning, which just tries to clone whatever you pre-recorded. And a cool one is generative adversarial imitation learning, which takes an adversarial approach to what you have pre-recorded. So it kind of tries to, be the enemy, the nemesis of what you have pre-recorded, and learn from that. So it's also a pretty smart approach of implementing such algorithms. So agents will be in a 3D world, and they're going to be making observations. They're going to be looking around. And there are a couple of observation types supported by Unity, by the ML agents package. Vector observations, which are basically numbers. So you collect numbers and you send them to the Python trainer. Visual observations, which is really what the camera is seeing. So it's gonna capture an image of the camera and send that to the Python trainer. Or raycast observations, which will be shooting a ray or a laser, if people don't know what a ray is, from point A to B, and will record what it hits and send that to the Python trainer. And they're also working on grid observations, where you can set up a grid and see what's on every single tile, so that's also pretty cool. But that's quite a lot, especially for the 40 minutes I have. So today we'll be focusing on reinforcement learning using proximal policy optimization and vector observations. And we'll be doing cool things with that. A couple cool ideas what I would want to do. You have to train your agents to do what you want to do. And this is really what happened with my own agents. I don't think I've ever gotten mad at a computer as much as I did building these demos. Before you start, you need to design your agent. So what do I want to observe and what do I want to do? And they all have a certain loop. And this is pretty much the loop that all the machine learning agents are doing. They're going to be making observation, which can be positions, rotation, any flow number, distances, you name it. And then based on that observation, a decision is going to be made. And we can allow them to take actions between decisions or not. And the decision period is typically every frame within Unity. When a decision is made, they're going to act upon that decision. And continuous actions or discrete actions are basically what you're getting from the Python trainer. And the continuous actions are, just numbers, float numbers, which you can map to whatever you want. And discrete actions are actually branches on top of those float numbers. So you can if you have like two discrete actions, 0 and 1, you can say, okay, when this is 1, I want the character to be able to jump. So then it's going to jump and move at the same time. Otherwise, it's going to be only movement, jump, and then movement again. And finally, you have the reward structure, which is anything between -1 and 1. -1 being the punishment, 1 being the reward, and 0 is neutral. All right, so, let's get to the fun part, I would say. Everybody knows that pirates love treasure, right? So the idea is if we had a pirate, if we had a pirate and a treasure, that the pirate will find his way to the treasure. If he reaches the treasure, we give him some candy. And if he moves outside of the learning environment, we are going to punish him. And like that, hopefully he's going to learn that he needs to go to the treasure as fast as possible. The observations we'll be sending to the Python trainer are the position of the pirate and the position of the treasure. And the actions that we'll be requesting from the Python trainer are a float number for the x-axis movement and a float number for the z-axis movement. Unity is a little bit weird that way. You would expect this to be x and y, but I is like up in Unity, so it's the flipped axis. Oh, spoiler alert. So this is Unity, our game engine. This is our pirate. Couldn't use Jack Sparrow because of copyright and stuff. But this is our pirate, and this is our treasure. And we're going to teach him how to go to that treasure. If you look at the script, this is pretty much how it looks like. It's very easy to get started. All you need to do is inherit from the agent class, and then you already have an agent, and then you need to override some stuff. The first thing that we're going to override is the onActionReceived method. And here you can clearly see, hey, I'm getting two float numbers here, and I'm mapping it to the x and z position of the agent. Furthermore, we're going to collect some observations. And here is the local position of the chest and the agent. It is very important to use local positions, and I'll show you in a bit why. When the episode begins, we randomize the position of the pirate and the chest. Anybody got any idea what would happen if we didn't randomize the positions? Thank you, yes. Well, I didn't have that idea when I started, so I was like, whoa, this works very fast. And then I moved the treasure, I was like, hey, you dumb, that way. And so I randomized the position so it actually learns to go to the treasure, not just move from left to right. Some heuristics, not very important for now. And the onTriggerEnter is basically a Unity message that is being sent when a physics body collides or enters a trigger of another physics body. So in this case, we have our agent, which is a physics body, and if it collides with a goal, the treasure, we're going to set a reward of 1, so we're going to reward it, and then we're going to end the episode, so then it can restart, and if it hits the wall, it's going to be a punishment of -1, so maximum reward or maximum punishment, pretty much. All right, if you look in the editor, here basically you can say, I can't zoom it in, I hope everybody can see it, but you can see the vector observations, space size 6. So here we say, okay, I'm going to send you 6 numbers. And now we had 2 positions. We had the XIZ position of the agent and the XIZ position of the treasure. So that is 2 times 3, 6. And actions, I'm saying I want 2 actions for you, two numbers. That's mostly what's important here. All right, then we can go to our command line. And then we'll go to ML agents learn, run, ID is yarhar or something. And now you can see that the Python trainer is ready to receive messages from Unity. And then here we can press play. And here you can see that the agent is slowly being trained. If the rug turns green, that means it hit the treasure. But since it's red, you can clearly see it's always going out of bounds because it mostly is receiving random numbers and just going places until it finds what it's supposed to do. So yeah, like this, it would take some time to train it, right? Fortunately, we can speed it up. Let me close this. By parallelization. Did I pronounce that right? I think so, right? All right. So basically, this is the reason why you want to work with local positions instead of world positions, Because if you do everything based on local positions, so positions relative to the learning environment, you can duplicate your learning environment how many times you want, and it's still going to learn what it's supposed to learn, go to the treasure that is relative to your learning environment. And then we can restart it and resume from where we left. And now you can see them all moving. It's some Black Mirror thing here, huh? Trapped for all eternity, trying to find the treasure. But you could see, you can see it hangs a couple times. That means that stuff is being sent to the Python trainer and being received. So you can call it a little bit like garbage collection in the JVM. And you can see some green rugs appearing. That means those were successful. Then if you look here, you can see you get a nice info of the mean reward, which is minus 0.7 right now. And if your learning environment works and everything is going as expected, this should become lower and grow towards the 1. As you can see here, it's already at minus 0.0, pretty much. All right. Now, at some point, you're going to be happy with what you've done. And you're going to be like, OK, this works. So let me turn this off. Back to our single pirate. All right. And then in your results folder within your Unity project, you're going to have yarhar. And then you're going to have an .onnx file, which stands for Open Neural Network Exchange. And this is basically the brain we just trained. And in Unity, we can assign that one here. We can assign that to our agent. And now if we press play, I have this pre-trained because I wouldn't necessarily be able to train them in the 40 minutes I have. You'll see that our little Jack Sparrow, hopefully, slowly but surely, goes to the chest. And there we go. He's really trying, okay. And yeah, you can see it worked. He wobbles a little bit, so there is you could do something with a reward structure to train your model to not wobble a little bit, to just go as fast from point A to point B, or from origin to destination. But this works pretty well, and this model was trained maybe in 5 minutes to 6 minutes. So it's a pretty simple model. All right. Now, I make it my personal mission is to incorporate explosions in every single presentation I give. So, and everybody knows that cool people do not look at explosions, right? So that is exactly what we're going to be building. We're going to have a cool person, and we're going to spawn a barrel, and that barrel is going to explode after 5 seconds. If it's looking at the barrel at the time, we punish it. And if it looks away from the barrel, we're going to give it some candy, pretty much. That's it, right? So how are we designing this? We're going to be making pretty similar observations. Now we're going to observe the position, and this time also the rotation of the person. And then we're going to observe the position of the barrel. And the actions, actually this time we're going to be asking only for one action, and that is one number for the y-axis of the person, of our agent. So we're going to having the agent just moving forward all the time, and we're just going to be rotating it, or her. Yeah. Oh, let me start this up again. So then we go to our scene. There we go. So this is our learning environment, pretty much. Again, I have it duplicated for training reasons, but I showed you that one. And if you look at the agent, we're asking for, we're saying, okay, we're gonna give you 10 observations. 3 are XYZ position of the agent, another 3 XYZ position of the barrel, and then 4 are the rotation values of the agent, which is a quaternion. I don't know if anybody ever worked with quaternions. If you haven't, stay away. It's not fun. And then one action we'll be doing is, we'll be getting is the one float value for the I-axis rotation. Now, if you look at the code, here we get the action and we rotate our agent based on that number, pretty much. These are the observations I just said that we're collecting and sending. Once it starts, once the episode starts, we spawn the barrel and we start a timer for 5 seconds and then it explodes. And then we reward based on how the agent is looking. And the reward is actually pretty simple. We take the dot product between the agent and the barrel. So if the agent is looking directly to the barrel, the dot product would be 1, and we flip it to -1. And if the agent is looking away from the barrel, the dot product would be -1, and we flip it to 1. And that is pretty much our reward. So yeah, I think we can just immediately start a training run. What should I call it? Boom, boom, boom. All right. It started, right? Great. And then we can press play. And then you can see, bam. Maybe I should have added some restrictions so that she doesn't start walking on water. But cool people also walk on water, I guess. So yeah, and here you can see a little debug to see if she was being cool or not when the explosion occurred. So yeah, this works pretty well. And of course, you can parallelize it to speed up training times. This took, I think, maybe half an hour or something to train to something where I was like, okay, this is good enough. And eventually it looks something like this. Bam. Come on, there we go. Bam, as it's, could look at it all day. All right. So until now, we've been working with single agents, and it's pretty cool to know that you can also use multiple agents within the same learning environment. So I think, okay, what can I do to implement multiple agents? Well, back then I was reading Harry Potter, so Quidditch it is. Anybody that has no idea what Quidditch is in Harry Potter? Okay, good. So we have a wizard and a snitch. The goal of the wizard is to go to the snitch, and the goal of the snitch is to stay away from the wizards as long as possible, right? If the wizards catch the snitch, that is when they get rewarded, pretty much. And if the snitch survives long enough until, I think it's almost a minute that it needs to survive, it's rewarded. The observations that we'll be making are, and if they leave, the Quidditch field, we punish. This is not part of the official Quidditch rules, but I had to add this. So the observations we'll be making for the wizard, because there are two separate agents. The wizard is going to looking at his own position, the position of the snitch, and the distance between him and the snitch. And we're slowly rewarding it every time it gets closer. And the observations the snitch is making is actually pretty much the same, but flipped. And the snitch is also looking at the positions, the boundaries of the Quidditch field. Because if the snitch doesn't fly out of the field, then the wizard shouldn't fly out of the field either, was the original idea. The actions are pretty much the same, but now we're also going on the y-axis, so now we're going full 3D. up, down, left, right, forward, and backward for both. So we're asking for each agent, we're asking 3 actions. Oh, again, spoiler alert. All right, so we have our Quidditch scene. All right. Yes, it looks straight out of the movie, I know. No, I do not work for Warner Bros. So we have, Gryffindor over here versus Slytherin. Or, I mean, we are in Greece. We can also say Olympiakos versus Panathinaikos. And up is our snitch, all the way there, as small as it can be. And I won't go through the code because it's fairly similar to the previous two. But basically, once you start this, it's going to look a little bit like your wizard, Harry. Yeah. All right. And then once you start training this is what happens. I added some trails so I can actually see what's happening. So yeah, this is pretty trippy, right? I saw that accidentally the snitch flew into the Slytherin one and got a point. But yeah, so for the first hour, this is all you're gonna be seeing. At least that is what I was seeing. Until at some point it starts understanding, okay, I really don't wanna be close to these guys. And then it starts going flying away, and then the other agents are going to be like, hey, I really want to be close to that snitch. And they're going to start following the snitch. And again here, let me stop this, perfect. And again here, I also did a nice parallelization trick, to speed up training. Thankfully, I have a pretty beefy machine, which allowed me to do this. But yeah, this one took a long time. I think this one took almost a full workday to train to a point where I was like, okay, this is pretty cool. This works somehow. And then if you start it with a pre-trained model, here we go. El Clasico. So you can see the snitch flies up to the right, and then we have our 2 wizards flying behind it with all their might, and Gryffindor scores the first point. And again, you can see the snitch flying to the top right, and then the wizards following, and Slytherin scoring the point. Again, you can see the snitch flying to the top right, so there is something happening here. So after all those hours of training, the snitch learned, okay, I can stay alive the longest by going top right first, for some reason. But yeah, that is what he trained, so yeah, who am I to argue? But yeah, this could be probably improved by randomizing the starting position of the snitch, at least, instead of having it being at the same place all the time. And eventually, I had to nerf the snitch. It is slightly slower, than the wizards, because they were never catching it. It was just too fast. But there are also other ways of doing that instead of, cheating a little bit. All right. Then here. And then I was like, hey, Matrix is a cool movie. I bet I can do that. Anybody that have never seen The Matrix? Okay, good. So we're going to be dodging Matrix, bullets Matrix styles, like Neo in the first Matrix. We'll be doing a lot of observations here. If Neo is hit by the agent, we punish. More than he is punished for actually being hit, so punishment on punishment. And if he manages to do something like this and, and dodge the bullet, we reward. The observations we'll be doing are the bullet position and the nozzle position, so how is the weapon aiming and where is the bullet, and basically everything regarding the body of Neo. So its forward direction, the strains on all the joints, rotation deltas of the hips and the ankles and everything. And that's 182 observations in total we'll be collecting from the body and sending to the Python trainer. And the actions we'll be taking are basically rotation and strength of the joints. So we'll be rotating the joints to rotate his arms, neck, shoulders, and give it more strength, so to go more on the backside and things like that. So for the gamers here, they already probably realized this is a ragdoll, as in physics. And ragdolls are very unpredictable, and we're basically going to be controlling a ragdoll, or having a machine learned algorithm control the ragdoll. All right. So let's go on our Neo scene. Do you know what I'm saying? All right. So this looks a little bit familiar, I would say, right? Here is our Neo. No leather jacket, only a leather cape. Good enough. And this is our agent with a full automatic gun. And she's going to be shooting bullets. And then if we are training this, it's going to look something like, okay. Take the red pill, take the red pill. There we go. And start it up. All right. And this looks a little bit like this. This has to be the best rave party in town. So yeah, what you can see here is basically what I'm doing is I'm punishing the agent every time a body part touches the ground. So first he needs to learn to stand, and then needs to learn to dodge the bullets. So every time anything but the hands or feet touch the ground, I'm punishing and resetting the whole episode. And this looks, if I slow it down, this looks a little bit like this. So it's like over and over again. And this took a day and a half pretty much to train. Learning to stand is actually pretty difficult. I don't know if you remember. And at some point you'll have something that looks pretty good, and that's gonna look like this. So yeah, so you can already see the mistake I made here. Huh? I let him use his hands. But it's still very cinematic. So, is this going to be a hit? Ooh. Oh, yeah. So it's not 100%. But as you can see, there are two mistakes I did. First, I was treating the ragdoll as an actual person. So the constraints and strengths were those of what an actual athlete can do, or a person can do. And in retrospect, what Neo did in the movie wasn't necessarily believable. So that was a little bit tricky. And I let it use its hand. Or better said, I forgot to exclude the hands. So then it learned, hey, I can just do this neat little trick, and it's good. And yeah, a final one. I like heavy metal. I'm a metalhead myself. And I was like, hey, can I do something where the machine learning agents react to the music that is happening around them, so that they are taught to react to the music? And I was like, well, I mean, when I react to the music, I headbang, so pretty much I can teach them to do exactly the same thing. And because of time, I won't go too much into that one, but I do want to show it. So we have our scene here. I hope the sound works, and I hope it's not too loud. Otherwise, well, people that like metal, you're welcome, and people that don't like metal, sorry. It's perfect. Okay, so you can see there is some music playing. You can see, well, the frequencies on the back. You can see them headbanging. The song gets a little bit slower now. Even the lights react to that. And then the headbang becomes very slow. You know, there's not much to headbang. A little glitch there on the extremes, but that's fine. And then at some point, it's going to be, the metal starts going to kick in. And you can see. And I mean, if you have this technology, why would you ever go to a concert again? You just build your own concerts, right? Yeah, that was all I had. I hope I inspired some people to try to give this a try, to get into machine learning. It was definitely the most fun way of getting into the technology myself. So thanks for watching. If there are questions, shoot. And that's where you can find me. And don't forget to vote if you liked it or didn't like it. I mean, it's fine. It's the only way to get better. Thank you. Right, any questions? Yeah?
I don't know if it's not a technical question, but I think you might find it interesting anyway. Do you have any suggestion in how you can get a kid to get interested and maybe start experimenting with that instead of just playing a game? Because I know that there must be, there is always a way for an adult to start learning and experimenting with this, especially if you have a background.
You can try RPG Maker or Game Maker. There are very low-code platforms for an easy click like Scratch for programming languages for kids to get into. You could give that a try. Or Minecraft and have them use the red blocks. I think they use the binary blocks. It's also a good way to get into programming. So one more question, because my colleague is working. Yeah?
How do you stop the training?
How do you stop the training?
When the training is good enough?
Well, so at the beginning, I showed you the mean reward. At some point, when the mean reward is 1, you know, okay, this is as trained, as good as it can get, because it won't learn anything new, because the mean reward is already on 1. For example, the matrix example, it never reached 1. I think the mean reward ended on 0.8, and that's also why you saw that sometimes they still get hit. But at some point, you just gotta say enough is enough, I would say, and you reiterate on your reward structure and things like that. But I would say if your reward is between the 0.8 and 1, your mean reward, then your model is trained as good as it can. All right, thank you very much.